A coastline does not simply rise by several feet within moments without raising profound questions about the forces responsible. When residents along the Galfa Point and Cedros shoreline in southwestern Trinidad awoke to an unfamiliar landscape after the powerful earthquakes that struck northern Venezuela on the evening of June 24, 2026, they encountered far more than an ordinary aftermath of seismic activity. Sections of seabed that had previously rested beneath coastal waters were now exposed to the open air. Fish, crabs, clams, stingrays, and other marine organisms lay stranded across freshly revealed sediments. Cracks marked the shoreline, bubbling pools appeared where none had been noticed before, small landslides scarred nearby slopes, and natural oil seepage became visible in locations where geological processes seemed to have abruptly accelerated. Was an entirely new section of coastline emerging. Did the earthquakes permanently reshape part of the southern Caribbean? Or were observers witnessing the temporary expression of deeper geological forces that had been building for centuries before finally revealing themselves in a matter of seconds? Those questions quickly spread beyond Trinidad and Venezuela because the earthquakes responsible were not ordinary regional tremors. Within less than 1 minute, northern Venezuela experienced two exceptionally powerful earthquakes located southeast of Umare. The first registered a magnitude of 7.2 at a depth of approximately 66 feet, or about 20.3 kilometers. Moments later, an even stronger magnitude 7.5 earthquake struck nearby at a shallower depth of approximately 33,000 feet, or about 10 kilometers. Together, the closely timed events formed what seismologists commonly describe as a seismic doublet, an uncommon sequence in which two major earthquakes of similar size occur in rapid succession within the same region. The close timing of the earthquakes immediately attracted international attention because earthquake doublets often present greater geological complexity than isolated events. Instead of a single rupture redistributing stress throughout the surrounding crust, two large ruptures occurring within less than 1 minute can alter stress patterns across a broad section of an active fault system. That process has the potential to influence nearby faults, destabilize submarine slopes, and produce localized deformation extending well beyond the immediate epicentral region. Northern Venezuela occupies one of the most tectonically active portions of the Caribbean because it lies directly along the complex boundary separating the Caribbean plate from the South American plate. Rather than converging head-on, like many well-known subduction zones around the world, these two enormous slabs of Earth's lithosphere primarily slide past one another in a horizontal direction. Even though that movement appears relatively slow on a yearly basis, the accumulated strain over decades and centuries eventually becomes enormous. Measurements indicate that the Caribbean plate moves eastward relative to the South American plate at approximately 0.8 of an inch per year, or about 20 millimeters annually. While that annual displacement appears insignificant when measured over a single year, the steady motion continues relentlessly without interruption. Over generations, rocks locked together along major faults accumulate tremendous elastic strain until their strength is exceeded. When that threshold is finally reached, stored energy is released almost instantaneously as an earthquake. Much of northern Venezuela accommodates this movement through an interconnected network of major strike-slip faults extending across the country's northern coastline and interior mountain ranges. Among the most significant is the San Sebastian fault system, which parallels much of Venezuela's northern coast and accounts for a substantial portion of the relative motion between the two tectonic plates. Extending farther inland is the Bocono fault system, another major structural feature that shares responsibility for accommodating plate movement across western Venezuela. Preliminary seismic analyses indicate that the larger magnitude 7.5 earthquake was consistent with shallow right lateral strike-slip faulting occurring along this active plate boundary system. Right lateral strike-slip motion means that observers standing on opposite sides of the fault would see the opposite block moving toward the right during rupture. Although such movement is primarily horizontal, the Earth's crust rarely behaves with perfect simplicity. Variations in rock strength, fault geometry, buried sediment layers, and nearby geological structures often introduce localized vertical deformation even when the dominant fault movement remains horizontal. That distinction is especially important in understanding why reports from southwestern Trinidad attracted immediate scientific interest. Strike-slip earthquakes are generally associated with sideways motion rather than dramatic uplift or subsidence. Yet geological observations following the earthquakes appeared to indicate that at least one section of coastline had experienced measurable vertical displacement. Rather than contradicting the strike-slip mechanism, localized uplift can occur where complex interactions develop between fault movement, sediment failure, and secondary geological processes. Southwestern Trinidad occupies an especially complicated geological setting because it lies only a relatively short distance from northern Venezuela across the Gulf of Paria. The region contains thick accumulations of soft marine sediments deposited over thousands of years by rivers draining northern South America. These sediments rest upon older geological formations shaped by repeated tectonic deformation associated with the Caribbean-South American plate boundary. Unlike solid crystalline bedrock, water-saturated marine sediments possess mechanical properties that make them susceptible to sudden movement during strong shaking. Under intense seismic loading, buried sediment layers can lose strength, shift downslope, or undergo rapid deformation. In some situations, the movement of one mass of sediment forces adjacent sections upward, producing localized uplift that may appear surprisingly dramatic despite originating from processes occurring only within relatively shallow sedimentary layers. That possibility gained attention after residents began documenting remarkable changes along portions of the Galfa Point coastline near Cedros. Images and videos circulating shortly after the earthquakes showed broad expanses of newly exposed seabed extending beyond the former shoreline. Marine organisms that normally remained underwater became stranded across mudflats and rocky surfaces. Fish were scattered among exposed sediments. Crabs and shellfish remained trapped outside their usual tidal environment. Stingrays rested upon newly emerged coastal ground that had previously formed part of the shallow seafloor. The ecological consequences became immediately apparent. Marine organisms adapted to underwater conditions suddenly found themselves exposed to sunlight and air. Species unable to return quickly to deeper water faced dehydration, overheating, and predation. Although individual mortality represented only one aspect of the event, the widespread exposure of marine habitats underscored that whatever process had occurred was capable of altering the physical environment within an extraordinarily short period. Residents also documented fresh fractures cutting across parts of the shoreline. Some cracks extended through recently disturbed sediments, while others appeared along nearby ground surfaces. Small landslides affected localized slopes where saturated soils had evidently lost stability during intense shaking. Pools containing actively bubbling water emerged in several locations, drawing additional attention because bubbling often signals gases escaping through disturbed sediments after seismic events. Natural oil seepage also became more apparent following the earthquakes. Southwestern Trinidad has long been associated with petroleum-bearing geological formations because hydrocarbons generated deep underground migrate upward through fractures and permeable rock layers over geological time. Earthquake-induced fracturing can temporarily increase permeability, allowing trapped gases and fluids to reach the surface more readily than before. While such seepage does not necessarily indicate newly generated petroleum, it frequently reflects changes in underground pathways through which fluids travel. Taken together, the exposed seabed, stranded marine life, fresh fractures, bubbling pools, landslides, and hydrocarbon seepage suggested that the coastal landscape had undergone genuine physical transformation rather than merely experiencing temporary tidal fluctuations. The combination of observations prompted rapid site visits by local geological specialists seeking to document the changes before weather, tides, and human activity altered the evidence. Among those examining the affected coastline was geologist Xavier Moonen, who evaluated the observed deformation and proposed that the uplift was consistent with a toe thrust associated with a reactivated submarine slump. That explanation focused attention not on the primary strike-slip rupture itself, but on secondary deformation occurring within unconsolidated coastal sediments. A submarine slump develops when large masses of water, saturated sediment, resting beneath coastal waters become unstable and begin moving downslope under gravity. Many submarine slopes remain stable for centuries because friction and internal sediment strength resist movement. Powerful earthquakes, however, can rapidly reduce that stability by shaking loose sediment layers, increasing pore water pressure, and weakening internal cohesion. When downslope movement begins, the front portion of the moving sediment mass can behave much like the leading edge of a slowly advancing bulldozer blade. Sediments accumulating at the lower end of the slump become compressed, forcing portions of the seabed upward. Geologists refer to that compressed leading edge as a toe thrust. Instead of simply sliding downward, part of the displaced material is pushed vertically, creating localized uplift that may permanently alter coastal elevations. According to this interpretation, the powerful Venezuelan earthquakes supplied the intense shaking necessary to reactivate previously existing unstable sediment deposits beneath or near the Galfa Point coastline. Rather than requiring large-scale vertical displacement directly along the main strike-slip fault, the uplift could have resulted from secondary sediment deformation triggered by seismic shaking. That distinction remains significant because it demonstrates that major earthquakes may reshape coastlines through multiple interacting geological mechanisms rather than through fault movement alone. Even so, one aspect of the reported changes immediately attracted careful scientific scrutiny. Estimates suggesting that portions of the coastline may have risen by as much as approximately 20 feet, or about 6 meters. Such a figure, if ultimately confirmed through detailed surveying, would represent an exceptionally large amount of localized coastal uplift associated with a sediment-driven process. At present, however, those estimates remain preliminary and have not yet been independently verified by national or international geological agencies. Ongoing field measurements, satellite observations, elevation surveys, and additional geological analyses will ultimately determine the precise magnitude and spatial extent of any permanent vertical displacement. The remarkable sequence of earthquakes recorded on the evening of June 24, 2026, immediately distinguished itself from the vast majority of seismic events observed around the world. Instead of one dominant earthquake followed by a series of much smaller aftershocks, northern Venezuela experienced 2 major earthquakes separated by less than 1 minute. The first measured magnitude 7.2, followed approximately 38 seconds later by an even larger magnitude 7.5 event. Their close timing, similar size, and nearly identical location southeast of Umare placed them within the rare category known as a seismic doublet, a phenomenon that represents one of the more complex expressions of tectonic activity along active plate boundaries. The first earthquake originated at a depth of approximately 66,600 feet, or about 20.3 kilometers, while the second occurred considerably shallower at approximately 33,000 feet, or about 10 kilometers beneath the Earth's surface. Although their epicenters were only a short distance apart, each rupture released an enormous amount of stored tectonic energy. The second earthquake did not simply repeat the first. Instead, it released additional stress that further reshaped the regional stress field, making the overall seismic sequence significantly more complex than a single isolated rupture. Understanding why northern Venezuela produced such an unusual pair of earthquakes begins with its position along one of the most active tectonic boundaries in the Caribbean region. Venezuela occupies the southern edge of the Caribbean plate, where it meets the northern margin of the South American plate. This boundary stretches for hundreds of miles across northern South America and continues eastward beneath the Caribbean Sea, forming an extensive system of active faults responsible for much of the region's earthquake activity. Unlike the spectacular subduction zones found around the Pacific Ocean, where one tectonic plate dives beneath another, the interaction between the Caribbean and South American plates is dominated primarily by horizontal motion. The Caribbean plate steadily moves eastward relative to the South American plate at an average rate of approximately 0.8 of an inch each year, or about 20 millimeters annually. Although that annual movement appears almost insignificant, tectonic plates never stop moving. Over decades, centuries, and even millennia, that continuous motion stores tremendous elastic strain within rocks locked along the plate boundary. The Earth's lithosphere behaves much like an enormous system of interlocking blocks. Friction prevents those blocks from sliding freely despite the constant forces acting upon them. As plate motion continues, stress accumulates until the rocks can no longer withstand the pressure. When their strength is finally exceeded, the locked fault ruptures, releasing centuries of accumulated energy in only seconds. That sudden release generates seismic waves that radiate outward through the crust and produce the shaking experienced during an earthquake. Northern Venezuela has experienced this process repeatedly throughout its geological history. The country's northern coastline marks one of the principal zones where the Caribbean plate accommodates its motion relative to South America. Numerous active faults extend across this region, each carrying part of the tectonic displacement generated by ongoing plate movement. Collectively, these faults form an interconnected structural network capable of producing destructive earthquakes whenever accumulated strain exceeds the strength of the surrounding rocks. Among the most significant members of this fault network is the San Sebastian fault system, which extends along Venezuela's northern coastline. Geological measurements indicate that this right lateral strike-slip fault accommodates approximately two-thirds of the relative motion between the Caribbean and South American plates in this part of the plate boundary. Its long history of repeated movement demonstrates that strain has been accumulating and releasing along this structure for millions of years. Extending southwestward from the vicinity of the June 24th earthquakes lies another major tectonic feature known as the Bocono Fault System. This extensive strike-slip fault traverses western Venezuela and forms another critical component of the regional plate boundary. Although the June 24th earthquakes are most consistent with rupture occurring along the San Sebastian structural system, the broader tectonic setting cannot be understood by examining a single fault alone. Instead, northern Venezuela functions as an interconnected fault province in which stress is continuously transferred among numerous active structures. The preliminary focal mechanism determined for the larger magnitude 7.5 earthquake indicates right lateral strike-slip faulting at shallow depth, consistent with the expected movement along the Caribbean-South American plate boundary. In this type of fault motion, the two sides of the fault slide horizontally past one another. An observer standing on one side of the fault would see the opposite side moving toward the right during rupture. Horizontal displacement dominates the movement, although local variations in fault geometry frequently produce smaller zones of compression, extension, uplift, or subsidence. Strike-slip earthquakes differ fundamentally from the megathrust earthquakes associated with major subduction zones, such as those surrounding the Pacific Ring of Fire. Megathrust earthquakes involve one tectonic plate being forced beneath another, often generating widespread vertical displacement of the seafloor capable of producing devastating tsunamis. Strike-slip earthquakes, by contrast, primarily involve lateral movement. Nevertheless, their destructive potential remains enormous because they frequently occur at shallow depths beneath densely populated regions. The relatively shallow depth of the magnitude 7.5 earthquake significantly influenced the intensity of shaking experienced across northern Venezuela and neighboring portions of the southern Caribbean. Earthquakes originating closer to the surface generally transmit stronger ground motion to nearby communities because seismic waves lose less energy before reaching the surface. In this case, the second earthquake's depth of approximately 33,000 feet, or about 10 kilometers, placed it well within the range capable of producing severe surface shaking over a broad area. The occurrence of two major ruptures in such rapid succession also raises important geological questions regarding stress transfer along the fault system. When a large earthquake ruptures a fault, it redistributes stress throughout the surrounding crust. Some neighboring sections experience reduced stress after slipping, while others receive additional loading that may bring them closer to failure. In certain situations, that redistribution occurs quickly enough to trigger another major rupture almost immediately, producing the rare seismic doublets documented in several tectonically active regions around the world. Although detailed analyses continue, the June 24th sequence appears consistent with such rapid stress redistribution. Rather than behaving as a conventional aftershock, the magnitude 7.5 earthquake likely represented a second major rupture occurring within an already evolving regional stress field. The extraordinary proximity in both time and location suggests that the two earthquakes formed part of the same broader tectonic episode, with each rupture influencing the mechanical conditions experienced by the other. Another important characteristic of northern Venezuela is the extraordinary complexity of its geological framework. Millions of years of plate interactions have folded, faulted, uplifted, and fractured the crust into a mosaic of mountain ranges, sedimentary basins, coastal plains, and offshore structures. The coastal range of Venezuela, running parallel to the Caribbean shoreline, reflects repeated episodes of tectonic compression and strike-slip deformation associated with the long-term interaction between the Caribbean and South American plates. Offshore, the geological picture becomes even more intricate. The Gulf of Paria and adjacent marine basins contain thick accumulations of sediment transported from the South American continent over thousands of years. These younger sedimentary deposits rest upon much older tectonic structures inherited from earlier phases of regional plate evolution. Strong earthquakes propagating through this complex geological environment interact differently with each rock type and sediment layer, producing variations in ground motion, deformation, and secondary geological effects across relatively short distances.